Our next speaker is Tianqi Xie from the Department of Geosciences, and she will be presenting The Impact of the Impact. What does the rock say?
Thank you. Why are we here? Partially, it's because dinosaurs are no longer here. Dinosaurs has existed for 1,165 million years ago. And 66 million years ago, they were wiped out by a giant impact. And the other life form, including us, got a chance to evolve and thrive on our mother planets, including us. But this giant impact is not the only impact that shaped our planet. Throughout the history of Earth, we have many, many impacts. Big impacts gave us the moon. Smaller impacts gave us a place to go in Arizona. And we are interested in those events because we want to understand what do they do to us, what do they do to the climate. But they're really hard to study. First of all, we were not a thing when such thing happens. So, fortunately, we have the rocks. The rocks have seen everything, but there's one problem. They don't talk. And some of the rocks doesn't remember either. So here is the rock that I'm talking about today. I'm dressed up like one. Feldspar, my favorite. You may have seen those in gift shop. They're everywhere. Why? Because they're one of the most common minerals in Earth's crust. And they're one of the very first mineral to crystallize when the Earth is lava. And they remember impacts, like a little photo album. They have all these micro features that recorded that impact has happened. And people are collecting samples and look at those, and right now we kind of have a faint feeling that these are indicators for impacts. And some are like higher shock than the other ones. But the thing is, we want to know precisely how they're formed. We want to reproduce these memories. And that's what I do. I reproduce these memories in feldspar with my brilliant friends. I don't have friends. Diamonds are my friends. I squeeze the feldspar in between diamonds. We heat them up using laser. Then we look at it under really bright light that is 100 billion times brighter than your normal X-ray. Then we got to see everything. The changes, the flare, the sparkle, and broken diamond. And here is the results from it. For the first time ever, not only we have the pressure range of how these features are formed, we have the temperature. And now, we were able to see, if you see such features in feldspar, you can say, oh, that reached almost 3,000 K for it to form. And you know how high temperature is 3,000 K? That's closer to the core of Earth. That's really high temperature. And 60 GPa, that's your mantle pressure. It's really high. And these can be all created on the surface of planets by impact. And you may wonder, what is this gap, right? Ladies and gentlemen, that's the fun part. Turns out, feldspar in this range, it's not feldspar anymore. It changed into assemblage of other minerals that people barely reported on Earth, but they are seen everywhere in meteorites from other planets and other galaxies. And that's partially why we are heading to the other planets and other galaxies in this century. We are heading back to the moon as we are speaking. We have a rover going on Mars. We have 3 more missions to Venus, just so we can find my feldspar on these planets. They do exist. We'll read their memories. We'll reconstruct their history. And eventually, all this information will contribute to our understanding of Earth, to our understanding of solar system. And eventually, we can put all the pieces of the puzzle together and tell you a better answer of the question of why we are here. But until then, enjoy life without dinosaurs. Thank you so much.